constituents, it can be analyzed by other sensitive methods. So here table 6.2 and 6.3, it shows the list of common metals that can be determined by this electrogravimetry. So applications of electrogravimetry by the using the constant current electrolysis, if the analyte is Ag plus, it can be weighed as Ag. The cathode has to be maintained as platinum, both the cathode and anode, and the conditions is alkaline Cn minus. Then we will get a good yield of Ag plus. So if we want to know about Zn2 plus, then it is measured. The output is measured in Zn. The cathode should be copper or platinum. The anode should be platinum, and the electrolytic solution must be acetic citrate solution. Then the good yield of zinc it can be done. So here in table 6.4, we can see the applications of electrogravimetry by constant potential electrolysis. So if the metal is silver, then the potential we have to maintain is plus 0.1 volt. The electrolyte should be taken is the acetic acid or acetate buffer, and the other metals that can be present with silver is copper and other heavy metals. So these are some of the parameters that we should that needs to be maintained while the extraction of the metal by potentiostatic electrogravimetry. Then coming to the separations. So how electrogravimetry can be used for separations uh, of one species from another. This method is used to remove interferences, particularly in electrochemical method. The controlled cathode potential electrogravimetry is very much useful in the quantitative determination of metallic species. Then simultaneous depositions. A mixture of copper and lead can be determined by the deposition of copper in the presence of nitrate ions at the cathode. Lead is deposited as lead oxide at the anode. Then, in preparative organic chemistry, if an organic compound can undergo a series of reductions or oxidation at each at a definite potential, then it is possible to reduce the starting material to the desired product by controlling the potential of the cathode during reduction. So this type of electrolytic reduction is much more economical than our other conventional reduction processes, where we encounter unnecessary side products. Then coming to application of coulometry. So this was about your electrogravimetry, and now this is application of coulometry. So the detailed theory, instruments and electrolytic cells we have discussed in the previous class. Now the basic relationship that is used in calculating the amount of the substance in a solution is given by M is equal to MR by 96500 into Q. So here MR, we remember it is the molar mass, small m is the mass of the substance, Q is the coulomb. That in of the coulomb is equal to I into T, that can be written here. So basically coulometry is two types of it is of two types, like coulometry with controlled potential and coulometric analysis with constant current. So in the first case, that is in the potentiostatic coulometry, the substance of interest it must react with 100% current efficiency at the working electrode, the potential of which it is controlled. Here in this case, in potentiostatic coulometry, the potential is constant. The completion of the reaction is indicated by the current decreasing to practically zero, and the amount of substance produced or consumed at the electrode is determined from the reading of a coulometer in series with the cell or with the help of a current time integration device. So in the second method, that is amperostatic coulometry, where the current remains constant, a solution of the substance to be determined is electrolyzed with constant current until the reaction is completed as determined with the help of a suitable indicator in the solution, or by using amperometric, potentiometric or spectrometric techniques. We know that Q is equal to I into T. So with this, the time can be measured accurately by using a stop flow or a slow inertia integrating motor unit. Then applications of coulometry. The coulometric method has considerable greater scope than electrogravimetry. It is it is we know that electrogravimetric methods, they are limited to the analysis of metals which can be plated out and weighed. On the other hand, in coulometric methods, they do not require weighing, and the reaction did not need not give rise to formation of a solid product. So further, coulometric methods are also not limited to the reduction of metal ions, but they can be used for any electrode process which can be operated at near 100% current efficiency. For example, controlled potential coulometry has been used to determine organic compounds such as trichloroacetic acid and picric acid. Coulometric methods, they are not limited to reduction process, but reactions taking place at the anode can also be studied by coulometric processes. In coulometry, at constant potential, normally a mercury cathode is preferred since the optimum control potential for a given separation is easily determined from the polarographic data with the DME, that is the dropping mercury electrode. In general, there is no advantage in employing a control potential of more than minus 0.15 volt. Some of the values, that is the halfway potential, it has been listed here. For example, for the element chromium, so the electrolyte must be zero point 0.5 molar sodium tartarate, and the volt, that is, it should be, the halfway potential should lie in the range of minus 0.09 to 0.16 volt. So this is some of the conditions we need to maintain. So control potential coulometric methods have been widely used in the determination of many metal ions. Roughly 55% in the periodic table, they have been determined by cathodic reduction of metal ions to the metallic state. More than 2 dozen metals, we know, they form amalgams with mercury. Thus, they are determined by controlled potential method using mercury electrode. So now to understand how this works, let us consider a general procedure. So what is the general procedure for performing coulometric determinations at controlled potential of the mercury electrode? The supporting electrolyte 40 to 60 ml is first taken in the cell, and the rapid stream of nitrogen is passed through the solution to remove the dissolved oxygen, that which is similar to that of polarography. The mercury cathode, it is involved through the stopcock at the bottom of the cell. So here the stirring is done, and the tip of the bridge of the reference electrode is adjusted in such a way so that it touches the stirred mercury cathode. The potential state is adjusted to maintain the required control potential, and the solution is electrolyzed with the flow of nitrogen until the current decreases to a very small constant value. The preliminary step of electrolysis will remove traces of reducible impurities. The current usually decreases to 1 milliampere or less after 10 minutes. So in known volume of 10 to 40 centimeter 40 ml of the sample solution is taken in the cell, and the electrolysis is allowed to proceed till the current decreases. Electrolysis is usually completed within an hour, and the Q value is measured by using this formula. Then separation of nickel and cobalt by controlled potential coulometer. So the reagents required are standard nickel and cobalt ion solution that has been prepared using nickel sulfate and ammonium cobalt sulfate. Then supporting electrolytes is 1 molar pyridine and zero point 0.5 molar chloride ion, and adjusted to pH 7 when silver anode is used, 1 molar pyridine and zero point 0.3 molar chloride ion. These are the requirements, and platinum is used as the cathode. So for the procedure for this process is, we will take 90 ml of the supporting electrolyte in the cell, and we will pass nitrogen through it to remove the dissolved air. Then the potential will be kept at minus 1.2 volt. Then, and the generally this process, it takes 20 to 30 to 60 minutes. Then the coulometer is attached, and the volume is adjusted, the potentiostat, to maintain the potential of minus 0.95 2 for nickel and minus 1.20 for cobalt determination. So then we will pipette out 20 ml of the sample solution that contains both cobalt and nickel, and we will continue the electrolysis under automatic control, which will take, with the time for this process will be minimum 2 to 3 hours. Then we will record the total quantity of current that has passed through the coulometers reading, and then using this formula we can calculate the amount of mass that has been deposited at the at each the electrode. So this is how we can calculate for the two metals, we can calculate the amount of deposited mass. Then the multi-step controlled potential electrolysis, the determination of several metal ions in the same solution is also by possible by this coulometry. So a sample solution, let us say, it contains several metal ions such as copper, bismuth, lead and zinc ions, which may be determined by this technique. So when the cathode potential is fixed at minus 0.008 volt, that then what at particular at this potential copper 2 plus is reduced to copper 0. So when the current the decays back to background, then the potential of the cathode is adjusted to minus zero point 0.3 volt. At this minus zero point 0.3 volt, bismuth 3 plus becomes bismuth 0. Then a lead 2 plus and zinc 2 plus can also be determined by their respective potentials. So with the help of this coulometry, multiple ion they can be detected and their mass can be known by using this formula. Then coming to microanalysis. So microanalysis is controlled potential coulometry is more popular than electrogravimetry because it avoids the final step of weighing the product. The tedious steps of dryings and weighing the electrode after each electrolysis process is avoided. This is why it is very useful, and it has an accuracy of zero point 0.5 plus minus 0.5%. Then coming to analysis of radioactive metals, the coulometric methods, they are widely used in the determination of uranium and plutonium, and thus they find extensive use in particularly in the nuclear fields. So the reduction of uranium oxide to U4 plus, it can be carried out in some H2SO4 medium with a mercury pool cathode at zero point 0.6 volt. The sample containing 7 to 75 mg of uranium, they may be analyzed and the accuracy is as low as plus minus 0.1%. So with such a high accuracy, this is coulometry is preferred for the analysis of radioactive elements. Then continuous monitoring of gas streams. Determination of trace level concentration of oxygen in a gas stream can be done by controlled potential analysis. The cell consists of a porous silver cathode and a cadmium anode. The reactions here, it has been given for this is the cathodic reaction and this is the anodic reaction. The porous silver cathode, it serves to break up incoming gases into small bubbles wherein the reduction of oxygen takes place quantitatively within the pores. The hydroxyl ions, they form during the reduction, they react with the cadmium anode and they form cadmium hydroxide product. A special feature of this setup is that a galvanic cell is formed and hence no external power supply is needed. Therefore, there is no need of a potentiostat to control the potential of the working electrode. The current produced is passed through a standard resistor and the potential drop is recorded. The oxygen concentration is proportional to this potential and the digital display can indicate the oxygen concentration directly. The setup can be used for the determination of oxygen in any gas stream and they can detect oxygen concentration from 1 ppm, that is 1 parts per million, to 1%. And then coming to electrolytic determination of organic compounds. So controlled potential coulometry, it offers a new step for electrolytic determination of organic compounds. That trichloroacetic acid and picric acid, they are quantitatively reduced at the mercury electrode. The coulometric methods, it permit the analysis of these compounds with an accuracy of 0.1%. So here you can see for these two types of reactions, for trichloroacetic acid and for picric acid, coulometric methods has been used for the analysis of these two very critical compounds. Electrolytic synthesis of new compounds. Even synthesis of new compounds and chemical species have been carried out using by the process of coulometry because it avoids the possibility of contamination. And then determination of the n values of the reaction. Even by coulometric methods, we can determine the n values of the reaction. Controlled potential coulometry can be used to determine the n values of the reactions. Determination of n values, it offers a route to deduce the kinetics and mechanism of the overall reactions. Picric acid is reduced at mercury pool cathode, in which n value of the reaction was found to be 18. So this product is identified to be triaminophenol, and this process, whole process was carried out by coulometric titration. Coulometry. Then now coming to application of coulometric titration. Coulometry at controlled potential has limited application because many substances do not undergo quantitative reaction at the working electrode. So when coulometry at constant current, the rate of change of substance that can be determined by is found to be continually increasing. This technique can be safely applied even in those substances which do not react quantitatively with a substance which is generated quantitatively at the electrode with 100% current efficiency. The quantity of substances reacted is called the Faraday's law. The quantity of electricity passed, it can be emulated simply from the time of electrolysis at that time. Coulometric titrations have been developed for almost all types of volumetric titration. So some of important titrations, coulometric titrations are: first is the neutralization reaction. That is the titration of a strong acid or a weak acids with hydrogen with hydroxide ions. Here 2H2O plus 2E forming 2OH minus. One of the main advantages of coulometric titration of acids is that difficulties that is associated with the presence of CO2 gas in the test solution or of the carbonate in the standard titration base, they are easily avoided. CO2 can be removed completely uh, from the solution by passing nitrogen gas before the titration is commenced. The presence of any substance that is reduced more easily than hydrogen ion or water at platinum cathode, or which oxidized will interfere. When internal generation cell is used with platinum auxiliary electrode, the latter must be placed in a separate component. 5.16. So here for the titration of acids, a silver anode may be used along with a platinum cathode in the presence of KBr as the supporting electrolyte. The silver electrode should also be placed in a separate compartment. It may be placed in a tube closed with the sintered disc as its lower and can be inserted directly into the test solution. So titration of a strong or weak acid in the hydrogen ions is generated at the platinum anode, as it has been shown by this reaction. Then coming to precipitation and complex formation titration. A large number of coulometric titrations have been developed in literature with the anode generation of Ag plus ions. The generating electrode consists of a heavy silver wire and a cell of the type shown in figure that was previously shown. So endpoint can be detected either with the adsorption indicators by potentiometry. Fluoride, bromide and iodine are best determined with mercury plus generated with 100% efficiency from mercury coated gold or from mercury pool anode. The endpoint is determined potentiometrically. In the titration of chloride ion, addition of methanol up to 70 to 80% is essentially in order to reduce the solubility of mercury 1. So for chloride, the standard potentials versus the energy of not of the potential couple, it involves uncomplexed Hg1 and Hg2. The oxidation of Hg to Hg2 2 plus requires a smaller potential. So Hg1 ions are the products when the mercury electrode is subjected to anode polarization in a non-complexing medium. Complexometric titrations using EDTA generated at a mercury cathode have been developed in the titration of solved cations. So the reduction of the ammonium mercury EDTA chelate at a mercury cathode was used to generate the Hy3 minus. Now since mercury chelate is much stable than the other metal chelates, then this cations titration of these cations are possibly done by this method. Coming to oxidation reduction titration, that is the redox titrations, the oxidizing reagents such as iodine, bromine, chlorine, SCE4, and the unusual oxidation states such as Ag2 plus, Mn3 plus, U4 plus, these can be generated by making use of the different coulometric titrations. So here, mm, the first is the coulometric titrations of redox titrations. They assume importance because of the possibility of in situ generation of unstable reagents such as bromine, dipositive silver ions, tripositive manganese ions, and others. Conventional volumetric analysis, they cannot handle or prepare these reagents. Electrogenerated bromine has been proven to be very useful for the determination of phenol, aniline, and mustard gas. A bromine solution is quite unstable and cannot be used as a titrant in conventional volumetry, and hence we use a Winkler's solution. So table 6.7, it provides a summary of the applications of coulometric titrations that involve neutralization, precipitation, and complex formulation reaction. Like for the determination of acids, that this is the normal electrode reactions and the secondary analytical reaction. For the determination of zinc, so this is the electrode reaction and this is the zinc determination reaction. In table 6.8, we see the summary of applications of coulometric titrations in oxidation reduction reactions. So the reagent is bromine. This is the general electrode reaction, and this is the substance that can be determined is phenol, aniline, mustard gas, and others. Like for the if the reagent is U4 plus, then the substance that can be determined is chromium 6 and cerium 6. So beside these applications, coulometry is also used to detect moisture in identical in industrial products, pharmaceuticals, food, petroleum products, and others. Then what are the advantages of coulometric titrations? The preparation, standardization, and storage of standard solutions are not necessary in coulometric titrations. This is useful especially for preparation of unstable reagents such as dipositive silver ions, tripositive manganese ions, bromine, chlorine, titanium, etc. It is easy to handle small quantities of reagents by coulometric titrations. By proper choice of current, micro quantities of substance can be analyzed with greater accuracy and ease. A single constant current source, it can be used to generate precipitating, complexing, and redox reagents. Coulometric titration can readily be adapted to automatic titrations as the current control is easily done. A number of automatic coulometric titrators are readily available in the market to monitor environmental pollutant. In chloride titrator, silver 1 generator is generated coulometrically. In sulfur dioxide monitors, anodically generated bromine oxidizes the analyte to sulfate ions. In carbon dioxide monitors, in which the gas stream absorbed in monoethanolamine, it is titrated with coulometrically generated base, and in water titrators, Carl Fisher reagent is generated electrolytically to determine the trace level concentrations of water content or moisture. So, in summary, we have seen that direct measurement of conductivity is potentially a very sensitive procedure for the determination of different parameters based upon the relative change in the conductance resistance of a solution with the addition of other electrolyte. Other methods have been developed for the titration of different types of mixed acid bases and their mixtures. Conductometric methods based upon precipitation or complex formation reactions, they are not as useful as those involving neutralization processes. The main advantage of the conductometric endpoint is its applicability to very dilute solutions and to solutions that involve relatively incomplete reactions. Electrogravimetric methods have been developed for the determination of various metal ions by controlled current and controlled potential techniques. The coulometric methods have wider application in determination of metal ions. This technique may also be employed in the determination of organic compounds. Coulometric titration have been successfully employed in the types of titrations like acid base, precipitation, oxidation, and complexometry. So, with this, the applications part of coulometry, electrogravimetry, and conductometry is over. We finish this unit. We'll just take a break of 5 minutes and then again start with the new unit. So now we'll start with a new unit that is about voltammetry. So here will the contents of this unit is the introduction, the electrodes and the processes, the different types of voltammetric processes, and their explanation, followed by the some of the terminal questions. So voltammetry, will first start with what is voltammetry, and then we will study what is cyclic voltammetry. So, voltammetry is the general name given to a group of electroanalytical methods in which the current is measured as a function of applied potential, wherein the polarization of the indicator or the working electrode is enhanced. For this, the working electrodes used in voltammetry, they are generally microelectrodes having surface area of few square micrometers to square millimeters. This field has been developed from polarography, which is a very particular type of voltammetry which uses a DME, that is a dropping mercury electrode, as the working electrode. Voltammetry includes all techniques in which the current potential measurements are made at stationary and fixed electrodes. The measurement of a current is done when the complete concentration polarization takes place in the electrochemical cell. Voltammetry has been developed from polarography. In voltammetry, the process of polarization is enhanced by using microelectrodes as the working electrodes. Thus, we can say that the electrochemical method in which the current is measured as a function of the potential applied to a microelectrode is known as voltammetry. These electrodes may be solid like gold, platinum, and glassy carbon or mercury. The electrode is formed by a drop of mercury from a fine glass capillary, and this technique is called as polarography. Other forms of working electrodes that are used are hanging mercury dropping electrode, the static mercury electrode, the thin mercury film electrode, and the glassy carbon electrode, carbon paste electrodes, and others. So, coming to the processes, various methods are assigned to the terms of voltammetry and polarography, which differ in their measuring techniques. Voltammetry is widely used for the quantitative analysis of trace metal ions at the micro level. This study of redox processes lead to the qualitative and quantitative analysis of heavy metals and some organic substances in solution. In addition to this aspect, this technique is very versatile for research purpose in the field of redox reactions, electron transfer mechanism, adsorption process, corrosion proof materials, new electronic processes, and production of the different types of batteries. So this is here in figure 7.1 some common types of microelectrodes, and there how they look like it has been shown. Then coming to common voltammetric methods. So the widely used voltammetric methods are direct current methods, that is which is further they it uses DC polarography, and DC polarography, linear sweep voltammetry, sampled DC polarography, hydrodynamic voltammetry. Then pulse methods is normal pulse voltammetry, differential pulse voltammetry, square wave voltammetry, cyclic voltammetry. Then the stripping voltammetry, which further consists of anodic stripping voltammetry, cathodic stripping voltammetry, adsorptive stripping voltammetry, and the D is alternating methods. So in the direct methods, the linear sweep voltammetry and hydrodynamic voltammetry is discussed. So what is LSV? That is the simplest type of voltammetry is LSV, or we call it as the linear sweep voltammetry. In this technique, the potential of the working electrode is varied linearly as a function of the time, and the current response is recorded. The scan rates are relatively slow, that is less than 5 MB per second, which allows the movement of the fresh analyte to reach the electrode surface, so that the electrode is always in equilibrium with the work solution. Let us consider one electron reduction reaction, that is A plus E, A which takes up E to form the B. So, and it obeys the Nernst equation. So, E is the potential of the working electrode and E0 is the standard electrode potential. So if the solution containing only A is taken in a cell and an applied potential of about 200 MV is applied, then a minuscule amount of current will flow to convert a small amount of A to B so that the Nernst equation is obeyed. The amount of current increases as the potential is approached to E0. So when E becomes equal to E0, then B is equal to A. That is, in other words, at E0, half of the A is converted to B, and so that the current is halfway to its limiting current. So here, as E is lowered further, all the A is converted to B as it reaches the electrode. So this figure 7.2 is a normal DC polarography, and this is the potential diagram that has been shown for the normal DC polarography. Then an important feature of this technique is that largest change in the slope it occurs around E0. The value of the potential corresponding to the point where the current is exactly half of the total current is known as half-wave potential, and this value is used to identify unknown species, and the difference in the value of the current from the start to the maximum value is known as limiting current. So polarographic determinations with higher sensitivity, they can be achieved if the ratio of the IF by IC is improved by measuring, by increasing the Faraday current or reducing the condenser current. These modifications give rise to sampled DC polarography and pulsed methods. So in normal DC polarography, the electrode area is not constant, and hence the current it fluctuates with the time of each drop. That is, here it is shown in figure 7.3. This problem can be alleviated by measuring the current at the beginning and at the lifetime of each drop. Now coming to what is sample DC polarography. So here in this technique, instead of recording current continuously, it was sampled for a particular time period just before the drop falls. So between the sampling periods, the recorder was maintained as its last level by means of a circuit, holding circuit. The major advantages of this current sampling is that it substantially reduces large current fluctuations due to continuous growth and the fall of drop at the dropping electrode. So here in figure 7.3 we see that the current near the end of the life of a drop is nearly constant, and it is only measured and the in the current sample technique resulting in a smooth flow. So LSV in which the solution or the electrode is kept in motion is called as hydrodynamic voltammetry. Then what is this hydrodynamic voltammetry? So in hydrodynamic voltammetry, the current is measured as a function of the potential applied to a solid working electrode kept in a stirring solution. The linear scan profiles, they are used while the solution is in motion towards the electrode. This cell, it has three electrodes. So the working electrode, that is mostly the mercury coated electrode, the reference electrode, that is the standard calomel electrode, and a counter electrode, which is a platinum coil. The current in the cell, it passes between the working electrode and counter electrode. The electroactive substance undergoing the electrode reactions at the microelectrode, it is brought to the electrode by three methods. First is the migration of the charged ions under the influence of an electric field due to the attraction of the electrode that has a positive or a negative charge, the convection resulting from stirring or vibration, and the third is the diffusion due to concentration gradient near electrode during the reaction. So that is this the current that is proportional to the concentration of electroactive substance and is given by I is equal to NFAD by delta into C of A. So here figure 7.5, it shows a three electrode cell for measuring the hydrodynamic voltammetry. So here the stirring is accomplished using a magnetic stirrer, but in other cases the electrode is rotated at a constant high speed in the solution, thus providing a stirring action. So the obtained voltammogram is a wave, and the current voltage plot is characterized by an initial residual current that grows up with increasing potential till the E half and then slowly increases till a stationary level is reached. At this value of potential, the ions reaching the electrode they discharge immediately. Thus, the concentration of the analyte in the diffusion layer is almost nil. So, another way of carrying out this technique, it involves the floating of the flowing of the analyte solution through a tube in which the electrode microelectrode is fixed. This technique has been used for voltammetric detector in HPLC. Some important applications of this technique has been the include the detection and determination of oxygen and chemical species like glucose, lactose, sucrose, etc. This detector has also been used in the fundamental studies in electrochemistry and detection of endpoints in electrometric and volumetric titrations. Then the pulsed methods. So what are the pulsed voltammetric methods? So there are four important pulsed voltammetric methods. First is normal pulse voltammetry, differential pulsed voltammetry or polarography, square wave voltammetry, and cyclic voltammetry. So first is the NPP, that is the normal pulsed polarography, or we can also say normal pulsed voltammetry. So in this technique, the potential is altered by using square wave potential pulses and is applied only briefly for about 50 milliseconds before each current measurement. The data obtained it has the same shape as the linear sweep voltammetry and the sensitivity is increased. The dropping mercury electrode it is held at the initial position until there are only about 60 milliseconds left in the time of the drop. Thus, very little electrolysis and depletion occurs. During the last 15 milliseconds before the expiration of the pulse time, the current is measured. Each new drop is stepped up to a greater potential and is measured about 40 millisecond delay. Thus, a sensitivity of approximately 3 times is observed. Then coming to the differential pulsed polarography. So it is an improved form where as it has been shown in figure 7.6 some different basic polarographic techniques. So in this technique 50 millivolt pulse is applied during the last 50 milliseconds of the lifetime of the mercury drop. The current is measured twice during the lifetime of each drop, firstly just before the pulse and second one just before the drop pulse. The difference in the current is plotted resulting in a peak shaped curve. The peak current in differential pulse voltammetry increases linearly with the concentration of the analyte. It also increases with the pulse amplitude but in a complicated linear fashion. In practice, amplitudes greater than 100 MV are not used since the peaks broaden and the resolution is significantly inhibited. So here in figure 7.6, some basic parameters in different voltammetric or polarographic units, it has been shown. The types of the current responses has been shown in this diagram. The higher deposition limit in this technique is due to the superior discrimination against the peak current and impurity Faraday current. Then coming to square wave polarography. This is a type of pulse polarography that offers the advantages of high sensitivity, great speed and low detection unit. The entire voltammogram is obtained in less than 10 milliseconds. It uses a potential waveform similar to one is this used in DPP and the entire potential sequence is applied during the lifetime of the single drop. The excitation signal in this technique is obtained by superimposing the pulse shown on the staircase signal. The length of the each step in the stair it is synchronized with the pulse period. Now for reversible reactions, a larger pulse is used so that its size is of great enough for the oxidation of the products to be formed. So the forward pulse it gives the cathodic current that is I1, while the reverse current it gives the anodic current that is the I2, and that the difference between these that is the delta I is equal to I2 minus I1 it is plotted to give the voltammograms. This difference is directly proportional to the concentration. The potential at the peak it corresponds to E half. It is possible to increase the precision of the analysis by signal averaging data from several voltammetric scans. Detection limits for square wave voltammetry, they are reported to be 10 to the power minus 7 to be 10 to the power minus 8 molar. The peak current in this technique is given as IP is equal to K into eta d to the power half into delta EA into concentration of the analyte that is Ca. Now coming to cyclic voltammetry. Cyclic voltammetry is an attractive method for the teaching of a number of concepts in electrochemistry. It is, in fact, one of the most versatile electrochemical techniques for the study of the electroactive species. The efficiency of cyclic voltammetry, it results from its capability to rapidly observe the redox behavior over a wide range of potential. The resulting voltammogram is similar to conventional spectrum. In it, it conveys information as a function of an energy scan. In spite of its wide applications, this technique is generally not well understood and as compared to other instrumental techniques. So here in figure 7.8, a typical cyclic voltammogram, it has been shown here. So fundamentals of cyclic voltammetry. It consists of cycling the potential of an electrode that is immersed in an unstirred solution of the electroactive species and then measuring the resulting current. The potential of this working electrode is controlled versus a reference electrode such as a standard calomel electrode or a silver-silver chloride electrode. The controlling potential which is applied across these two electrodes can be considered as excitation signal. The excitation signal for CV, it is a linear potential scan with a triangular waveform as it has been shown in figure 7.9. The triangular potential excitation signal, it sweeps the potential of the electrode between the two values, that is the between the two cycles, which is we call it as the switching potential. The excitation switch signal in figure 5.7.9, it causes the potential to scan negatively from zero point 0.8 to minus zero point 0.2. The scan rate as this is reflected by is 50 MB per second. A second cycle is indicated here by the dark line. So sometimes single or multiple cycles they can be used. A cyclic voltammogram is obtained by measuring the current at the working electrode during the potential scan. The current can be considered the response signal to the potential excitation signal. The voltammogram is a display of current versus potential. The since potential it varies linearly with time, the horizontal axis can be thought of the time axis. So this is how it is helpful in
Madam, one
understanding the
question.
principle of this technique.
Hello, madam.
Huh?
If from voltammetry, if will come one question means we need to write this all those theory or equation.
See, the question will come on any type of explain CV. Then you have to write everything. You have to draw the diagram of the voltammogram, the instrumentation, and the possible applications. So you have to write about that.
Okay, madam. Thank you.
Okay, these might be evil questions, but you might get about long questions. So then the the electrode we were talking about cyclic voltammetry. So here cyclic voltammetry, it has been discussed. If you look into this chapter, it has been discussed very briefly about the how we can measure the cathodic currents or the anodic currents and the potential. The formula has also been given in different parts, so you have to remember all this formula and write how CV is helpful in analysis of different redox reactions. So here in table 7.1, you can see the diagnostic test to decide the reversibility of a redox reaction by cyclic voltammetry. The criteria for reversible system has been shown here, and the criteria for quasi-reversible system, including the criteria for total irreversible system. So these are some of the criteria that needs to be remembered. Now coming to the instrumentation of CV. So CV requires a waveform generator to produce the excitation signal, a potentiostat to apply this signal to the electrochemical cell similar to polarographic cell, and a current voltage converter to measure the resulting current, and a XY reader or oscilloscope. So the first three items, they are actually all present together in a single device. The potentiostat, it ensures that the working electrode potential will not be influenced from other reactions or other interferences from outside. The data may be obtained with XY recorder at a slow scan, that is, let us say 500 millivolt per second, while the storage oscillator oscilloscope at faster rates having up to 20,000 volt per second. So here in figure 7.11, the instrumentation, basic instrumentation for CV has been shown. This is the O represents the working electrode, to reference electrode, to the auxiliary electrode has been shown. So modern potentiostat, they use a three electrode system that we know. We are today's world, we are directly dealing with the three electrode system. The potentiostat, it applies the desired potential between the working electrode and the reference electrode. The working electrode is the electrode on which the electrolysis of interest takes place. The current required to sustain the electrolysis at the working electrode is provided with the help of an auxiliary electrode. This arrangement prevents large current from passing through the reference electrode that could change its potential. A normal polarographic cell may be used in this technique. Such cells, they usually consist of glass containers which have a cap holes for introducing the electrodes. The reference electrode is the standard calomel electrode in the AgAgCl electrode. The auxiliary electrode is the platinum wire that is directly placed into the solution. Since the peak current in the voltammetric techniques is temperature dependent, the cell should be thermostated. The cells, such cells, they are commercially available. A large variety of working electrodes have been used in voltammetry. The DME, or that is the dropping mercury electrode, it is used specially in polarography, and the HMDE, that is the hanging mercury drop, is particularly used in cyclic voltammetry. So a thin coat of mercury, it can be deposited on the substrate such as graphite to form a mercury film electrode. A significant advantage of mercury lies in its good negative potential range. So in conclusion, we can say that CV has become increasingly popular in all fields of chemistry as a means of studying of redox states. This technique, it enables a wide potential range to be scanned rapidly for reducible or oxidizable substances. This capability, together with its variable timescale and good sensitivity, makes this the most versatile electrochemical technique. At the same time, it must be emphasized that its merits are mainly in the realm of qualitative or diagnostic purpose. Quantitative measurements are best obtained via other techniques, that is the pulse technique. Due to the kinetic control of many cyclic voltammetry experiments, some caution is advisable when evaluating the results in terms of thermodynamic parameters like measurements of E0. Then coming to stripping methods or the stripping voltammetry. So, stripping voltammetry is the most sensitive electrochemical technique for the quantitative analysis of micro-quantitative electroactive analytes which oxidize or reduce reversibly at solid electrodes or from insoluble species at the electrode surface. Basically, two steps are involved in this technique. The analyte is electrolytically deposited on the working electrode by controlled potential electrolysis. A reverse potential seal or stripping step is applied in which the deposited analyte is removed from the electrode. The final step is basically pre-concentration or electrodeposition, while the second one is the stripping step. So three different types of stripping voltammetry are possible. First is the anodic stripping voltammetry, the second is the cathodic stripping voltammetry, and the third is the adsorptive stripping voltammetry. So first is ASV, that is the anodic stripping voltammetry. This technique, it is used to determine the trace amounts of metal ions that can be pre-concentrated at an electrode by reducing to the metallic state. The microelectrode, it behaves as a cathode during the deposition step, and an anode during the stripping step, while the analyte being oxidized to the original form. So this may be explained in detail by taking the case of Cu plus 2. The deposition reaction at HMDE, it held at a cathodic potential, so that Cu2 plus 2E, it becomes Cu, where copper is amalgamated with the mercury. Since it is the HMDE, so copper is obtained as Cu and Hg. This step is basically a pre-concentration step where the metal ion, it forms a large volume of the solution, is concentrated at a small volume on the electrode. The solution is now stirred to increase the rate of the deposition. When the potential becomes positive, in the second step, the potential is scanned anodically towards the more positive potential. When the potential becomes positive, the analyte is stripped from the electrode, which returns to its oxidized form, that is Cu amalgam becomes Cu2 plus, and the current at this step is monitored as a function of potential, giving rise to the voltammogram. The peak of the current is proportional to the analyte concentration in the solution. This technique is very sensitive to experimental conditions. So this figure 7.12, it shows the details of a stripping voltammetry. In anodic stripping voltammetry, the determination of the analyte is based on the anodic dissolution. This process is followed voltammetrically, and the peak current is obtained. The peak current thus obtained is proportional to the potential scan rate and radius of the mercury drop. Then however, in both the cases, the peak current depends on the accumulation time, and therefore it is proportional to the concentration of the analyte in the amalgam. So then coming to cathodic stripping voltammetry. So here it is used for the determination of anions that form insoluble mercury salts at the mercury surface, or insoluble silver salts on a silver electrode. The experimental design is similar to that of an anodic stripping voltammetry, but with two modifications. The decomposition step involves the oxidation of the mercury electrode to Hg2 plus, which then reacts with the analyte to form the insoluble film at the surface, that is Hg2Cl2. The second step, that is the stripping, is followed by scanning cathodically towards a more negative potential, such that the Hg2 plus, it goes back to Hg, and the returning the analyte to the solution. Then the third is the adsorptive stripping voltammetry. So in this technique, analyte is adsorbed on the electrode surface, and there is no electrolysis step, and after complete deposition, the potential is scanned in anodic or cathodic direction depending on the type of analyte which is to be oxidized or reduced. The deposition step in this method, it amounts to an electrochemical pre-concentration of the analyte, that is, the concentration of the analyte on the surface of the microelectrode is greater than the bulk of solution, and hence these methods are extremely sensitive, and detection limit can be improved by factors of 10 to the power 6 from certain species. Now coming to alternating current methods. In this technique, the linear potential is modulated by a sine wave voltage of small amplitude. This produces an alternating current whose size is determined by the direct potential applied, and which is greatest at the half wave potential. So the plot of the measured AC current, it gives a peak shaped alternative current here in figure 7.13. It has been shown here. Then the basic instrumentation for voltammetry has been shown here. It consists of two important components. First is the 3-electrode polarograph, then the linear scan voltage generator to give different types of signals. Then the polarographic cell is made of 3 electrodes which are dipped in a solution containing the electroactive species and the excess of inert electrolyte, usually called as the supporting electrolyte. Then there is the working electrode. So the working electrode, it is usually a microelectrode whose potential is varied linearly with time. Then comes the reference electrode, which is normally a standard electrode whose potential is constant throughout the experiment, that is saturated calomel electrode or the AgCl electrode. And the third is the counter electrode, that is which is a coil of platinum wire or a pool of mercury that simply serves to conduct electricity from signal source through the solution to the microelectrode. The potentiostat, it allowed to impose the potential scanning between the working and reference electrode, while the current flowing through the circuit is recorded between the working and auxiliary electrodes. The computer CVT, that trace analyzer, has been used as an instrument with keyboard for such commercially available CB to it directly sends the scanning parameters and it handles the current potential output. Like in today's chemistry, we directly use automated CV. They directly display the result without the use of actually balancing the current. The computer automatically, the instrument automatically balances or handles the current potential output data. So, in summary, we have learned about the various types of electrodes, especially the common microelectrodes that are used in voltammetry. Various types of voltammetric methods have been discussed, also including the various discussion on different pulsed voltammetric methods has also been discussed today. So with this, the today's unit on this unit, that is on voltammetry, it is finished. So so I'll just start with the introduction with the next part. So the next unit, it deals with polarography and amperometric titrations. So the contents of this unit are the introduction to polarography, the different types of electrodes, the factors that affect the first is introduction to diffusion current, residual current, and the factors that affect the diffusion current, the polarographic equation, the estimation of the n values, the polarographic minima, maxima, quantitative and qualitative polarographic analysis, and the different types of amperometric titrations. So first, we'll start with what is the definition of polarography. The polarographic method of analysis, it was first developed in 1922. Then the current potential curves, they were called as polarograms, and hence the term polarography was introduced. So now we know, according to Ilkovic equation, diffusion current is directly proportional to concentration, keeping all other factors constant. So if some of the electro active material, it is present in the solution, it is removed by interaction with some other reagents, let us say EDTA, which is a common reagent, then the diffusion current, it decreases. So this is the fundamental principle of amperometric titrations or polarographic titrations. So most metal ions, they are reducible at the dropping mercury electrode, and multi-component mixtures can often be analyzed by selecting an appropriate supporting electrolyte, so that the halfway potential of the two ions are differed by about minus 0.2 volt versus the SCE. So based on this, polarography is used predominantly for trace metal analysis of alloys, ultra pure metals, minerals, metallurgy, environmental analysis, foodstuffs, and other clinical analysis. So even reducible anions such as BrO3 minus, bromate, iodide, chromate, and nitrate can also be determined using well buffered solutions by the process of polarography. So during electrolysis, the chemical reactions, they occur under the influence of a electromotive force at electrodes immersed in solutions. The reactions occurring at the electrodes, that is electrode reactions, they are characterized by the transfer of electrons between the electrode and the substances in solution. Because of this quality of positive and negative ions, they are balanced out, then but they are they are counteracted by oppositely directed positive and negative ions throughout the solution. So this is the current which is actually measured by the movement of electrons in the external circuit connecting the two electrodes. Therefore the current is the result of the electrode reaction. The electrode at which reduction occurs is called the cathode, and the electrode at which oxidation occurs, we know it is called as the anode. The curve that is obtained by plotting EMF applied to the cell against the resulting current is called as the current voltage curve. Here it is shown as a typical polarigram. In y-axis you can see it is the current. In x-axis you can see it is the applied potential. Now such current versus potential plot, IE curves we call them, they are actually called as polarograms. So when the applied potential is equal to the decomposition potential of the electroactive substance, then the cathode current start increasing due to the following cathodic reactions. That is, Zn2 plus will gradually it converts to Zn. Then the resulting zinc, it will form amalgam with the mercury on the surface of the mercury electrode. As the potential of the dropping mercury electrode is made more negative, there is a further increase in current in accordance with the Ohm's law, and the concentration of Z plus decreases at the electrode surface. So the process it continues. The number of Zn2 plus ions that diffuse from the bulk of the solution to the electrode surface is equal to the number that is deposited. Now when the applied EMF it exceeds the decomposition potential, the DME becomes depolarized because Zn0 has been formed. So now if we apply the Nernst equation, we can write it as E is equal to E0 plus 0.059 by 2 into concentration of Z plus. At the point C, here at the point C, there is no longer the current no longer increases, and the plot it becomes linear. At the point D, no increase in current is observed at the higher potential unless and until we apply a second compound. So from the point C onwards, the DME once becomes depolarized. Now because of this depolarized nature of the electrode, so the curve so obtained is called as a polarogram. So we see that it becomes polarized, again it becomes depolarized, and then we see that it is called, this is how the name polarogram comes into effect. Then comes the dropping mercury electrode. So this dropping mercury electrode will start in the next class. So this much for today. We'll again start with the DME in the next class.